Hello, this is Math 2270 coming to you from the College of DuPage for the summer of 2020. The title of this lecture is Fourier Series, some surface level observations about some pretty deep math and hints of wide-ranging. Let's begin by talking a little bit about the Taylor series that you studied previously. With Taylor series, you wrote a series representation of f of x. In terms of this, it was an infinite series. These were derivatives of all orders of the function, and you expanded in a power series. And one of the things you learned was, with some certain conditions, we'll talk a little bit about those, you were able to show that this converges to f of x on an interval for some r, but r depends on the function itself. It is always different for the function. Now, there's nothing wrong with this, but it does require that derivatives of all orders exist at the point. That's a big restriction. And also, r may end up being very small. So you have a good approximation only in a very small neighborhood of the point A of interest. And in fact, here were the conditions on this. The Taylor series will converge to f of x if this thing, which is r sub n of x, converges to 0 as n goes to infinity. Then this is actually equal. Now, another thing that was important is if and where it does converge, the convergence is sufficiently strong so you can integrate term by term and differentiate term by term, because you can do that with power series. Those were big deals, big results from your calculus studies. Okay, well, what we've learned about Fourier series is, and we were doing this informally, we were not proving anything. We just kind of say, well, suppose f of x was that, and we could multiply by the right things and integrate and take advantage of the calculations. But we'd say, well, informally, Bn, the coefficients look like this and this. Now, that is if it is an odd function. And by considering the extension of any function, whether it's even or odd, the odd extension of it, I guess what I'm saying is this coefficient here is true regardless of what f of x is. Similarly, if f of x was an even function, and we are informally doing this, we'd say, oh, if the coefficients are this, then things seem to work out. And if we consider the even extension of any function from 0 to L to minus L to L, the same final coefficient result may be achieved. We haven't proven anything, we just say informally the math seems to work. And now, and this is something we didn't talk much about, but if f of x is neither even nor odd, then we could think about doing this, having it be expanded in terms of sines and cosines. And informally, again, the calculation tells us that these are what the a's are, and this is what the b's have to be. Now, this is some pretty serious math, but what we learn is that if a function is not continuous but just piecewise smooth on this interval, the Fourier series will converge to the periodic extension of f of x if the periodic extension is continuous, and it will converge to the midpoint of the interval of the limit from the left and the limit from right otherwise, if there's a jump discontinuity there. Now, you see, this is a much broader kind of thing because piecewise smooth only says you have continuous first derivatives. It doesn't say anything, and it's piecewise. So this is a very general thing, and I want you to think about that L could be a very big number. The biggest number that you ever want to consider in your problem, L could be. So that means that the cosine series will converge, and so will the sine series. We haven't proven this, but you can take the derivatives term by term of both the sine and cosine in general, and you can also integrate term by term. But you should note that the new series that results from term by term integration may not be the Fourier series for the integral of the function that has to do with the constants of integration. So you see, this is much more general than the Taylor series. It's not a dinky interval. It could be minus L to L, where L is a big number, and the convergence is strong enough to do the things we want to do with the function. Everything we did when we were solving those mathematical physics problems was kosher. And we've only just begun. There are many applications of Fourier series. I'm just going to read the abstract of Hollingsworth's paper. The Fourier series, the founding principle behind the field of Fourier analysis, is an infinite expansion of a function in terms of sines and cosines. In physics and engineering, expanded functions in sines and cosines is useful because it allows one to more easily manipulate functions that are, for example, discontinuous or simply difficult to represent analytically. In particular, the fields of electronics, quantum mechanics, electrodynamics all make heavy use of the Fourier series, and we saw mathematical physics as well. Additionally, other methods based on the Fourier series, such as the fast Fourier transform or discrete Fourier transform, are particularly useful in digital signal processing, that is, speech recognition and other things, and spectral analysis. You may want to look up this paper because it might apply very heavily to your field. This also sort of justifies that our annihilator approach was maybe a little bit more rigorous than you might have thought. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.